All right, we've talked about new equations, new forms of equations of lines, and we've talked about equations of planes. We're going to spend a couple of days just doing stuff with planes. So looking at their properties, all the things that we know about them, just getting used to working with them. Like we said, um, from the equation, there's going to be all kinds of questions that ask you, not explicitly, but you're going to have to convert it to a different form of an equation. You're going to have to decide what's the best form to have. What information can you get from one form? How do you put that in another form? Like all those different kinds of questions. So we're just getting used to really the notation and thinking about planes. That being said, thinking about a plane. So this is the scalar form of the equation of a plane, and it has the normal vector ABC. So this is important, and just again, visualizing this stuff is so important. So let's take a look here. Okay, so there's our plane. It has a normal. And as I said, turns out the normal tells us a lot about the plane. It's really useful. Um, Scalar form is useful, and the normal is related to scalar form, so that's a good thing. The other nice thing about the normal is a single normal helps us define that plane, sort of, not uniquely, but it's a big part of it compared to direction vectors that you have to have multiple direction vectors to define a plane. Um, Direction vectors parallel to the plane. We don't really talk about direction vectors in a plane, okay, but these would be parallel. I could have direction vectors that are perpendicular to each other or not, right? I can have them not. So again, different direction vectors parallel to the plane may or may not be parallel to each other, perpendicular to each other, collinear, opposite direction, like all those kinds of things, right? And there's an infinite number of direction vectors that are parallel to the plane, whereas there's only one group of vectors that are normal to the plane, that are perpendicular to the plane, and they are going to be perpendicular to every direction vector that's parallel to the plane. So that becomes a really big idea. Okay, so we'll probably call this plane pi. It will have some points in the plane. And 3 points can define a plane. We talked about that. We're not going to go into that in any more detail right now, but those might be points in the plane. And let's say this is a point outside the plane. You know, you might have a point that's sort of above the plane or totally outside the plane, depending on how you're visualizing the interpretation, right? Or the orientation. And that being said, visualizing is so important. So let's take a look at this. So here is our 3 space, and here's our plane. Okay, and we looked at this before, and I've just set this up so that I can change sort of some of the coefficients involved in the plane, and so I can, you know, skew it a little bit in space, just so that we can see the different looks of it. Of course, if I had designed it in such a way that you could maybe spin it around and rotate it in sort of other axes as well, okay? I can move it up and down just by changing that constant. In fact, you can see it happening right there. Right? So, you know, by modifying the, the, the coefficients involved in the scalar equation, or of course in any other form, we can move this around everywhere in space, just like a line into space that we're very familiar with. This one has these 2 direction vectors. So notice that they are parallel to the plane. Now this plane happens to right now be going through the origin, but you know, there's no reason why it would have to. So I could have the plane not going through the origin, but there are the direction vectors. And notice that, again, vectors as a standard are thought of as starting at the origin, going to a point out in space. So that's kind of what we're looking at. and those two direction vectors do happen to be parallel to the plane and defining the plane. So if I change one of these direction vectors, notice how the plane changes along with it, right? The plane is always going to be parallel to both. Again, think about that. That's why two direction vectors that are not collinear, why they help define that plane. And then a point. So that kind of tells me, the direction vectors tell me the, sort of rotation of it, you could think of. And then the point can move it around like this, okay? So I'm going to put that back, and that brings us to the last idea. We looked at this before, points, right? So I can have a point that is in the plane, like this one here, and then I can have a point that is not in the plane, like this one here. Okay, and just for fun, we'll take a look at this in augmented reality as well.
All right, so this is going to be augmented reality version of the same thing. So first I have to detect the surface, get my axes, there they are, and then I can start putting my stuff on here. So there's the plane. We saw this before, same as just in sort of the 2D version on the computer. I can tilt it back and forth by just dragging these sliders, right? I can move it up and down if I want to. Let's see, I got to put that back there and put that back there, I think. I got a couple of points, and if I zoom in, I can see one of them is in the plane and the other one isn't. So this one up here looks like it's in the plane, and this one down here is not. Okay, hide those. And finally, let's see if I can find the vectors that are parallel to the plane. So they are parallel. They're not in the plane because I guess I moved it, but they are parallel to the plane. So let's see, there we go. So I can move that back and see that they're parallel. All right. So there's a whole bunch of the really important properties of the plane. I believe that is the normal. So it's hard to tell just by looking at it, but it is orthogonal to both of those. It's perpendicular to both, and it's perpendicular to the plane. I got that by taking the cross product of those two vectors parallel to the plane. Okay, so useful to visualize this.
All right, so now that we've talked about some of those ideas about planes, some of those properties of planes, the different ways of visualizing it, the different things that are important to think about, we're going to go back to just doing stuff with planes. Okay, and again, notice as you go through these questions, and then when you go through the practice on your own, how a question is worded in a certain way, but really ultimately it's asking you to do something specific. And part of, I think, the challenge of this unit or learning this stuff from the beginning is understanding what the question is actually asking you to do, because it's not always going to come out and tell you that. And that's a part of understanding the different forms of equations of lines and planes and the important properties that you can get from them. You want to know what you can get from scalar, what you can get from vector form, and how you can use that, turn it into other information that might be useful, right? That's the whole point. So the questions are not going to come out and just walk you through the instructions of how to do everything and what you're supposed to do. All right, let's get into this. Normal vector of a plane is given, 2, 3, 1, and a point on the plane is given. Find the scalar equation of the plane. All right, so the normal vector, what we want to know is those are the coefficients of the sort of three parts of the scalar equation of the plane. So I can write this as 2x plus 3y plus z plus d equals 0. Okay, and then use the point. So this one I would say is fairly straightforward. It gives you the normal vector and a point and just specifically says find scalar equation, but that won't always happen. It won't always be that straightforward. But if you want to find the normal, or sorry, if you want to find the scalar equation of the plane, this is how you're doing it, right? With a normal and a point, subbing in and solving for d. 2 times 4 plus 3 times 2 plus 5 plus d equals 0. And I believe turns out d is negative 19. And don't forget to restate the equation. Again, this is a common mistake in grade 9, and it continues to be a common mistake in this course. Minus 19, forgetting to actually state the equation, right? There you go, scalar equation. Is Q in the plane? If I wasn't asked to find scalar equation, and I was just asked to find if that a point is in the plane, I would find scalar equation of a plane in order to determine that, right? That's going to be the easiest way to do it. So that's the kind of thing that I was talking about, where you want to know that if it's asking you about checking a point in the plane, you just want to know you're going to use scalar form for that. And if you didn't have scalar form, you'd have to go and find it. So let's see, left side is 2 times 4 plus 3 times negative 1 plus 2 minus 19. So that works, and right side is just 0. This works out to negative 12, not equal to the right side. Therefore, Q is not in the plane. Okay, is vector A parallel to the plane? So this one is a little bit different. How are we going to figure that out? And we just need to know that this is asking us to do something specific. What's the easiest way to determine if it's parallel to the plane? Well, any vector that's parallel to the plane has to be perpendicular to the normal. It doesn't, if I go back up here, any particular vector parallel to the plane isn't necessarily perpendicular to other vectors or not, right? Like you can have some that are perpendicular and you can have some that are not perpendicular. You can have vectors that are parallel to the plane that are parallel to each other, collinear. So that doesn't tell us anything. But all the vectors that are parallel to the plane are all perpendicular to the normal. That's one of the reasons why, or that's kind of almost a summarizing why the normal is so much better than just any old direction vector that's parallel to the plane. So how are we going to do this? We're going to check, we're going to check A dot N. We're going to check the direction, the dot product. And if it's equal to 0, that means they're perpendicular, and that means that A has to be parallel to the plane. Okay, so and I think this works out to 5. Not 0, therefore, vector A is not parallel to the plane. So a question like this is asking just to do a dot product, which from a, computing that is very easy, but it's asking us to make connections with different properties of planes in general, this plane, its direction vectors, that kind of thing. Like that's important connections to make. So that's really what that question is all about. So find a vector that is normal to, another vector, that is normal to the plane, not parallel. So the one that we were given was 2, 3, 1. So what's some other vector that's normal to the plane? This is trivial in a lot of ways once you realize what this is really saying. Because any vector parallel to that will be normal to the plane. And those are the only ones. There's not going to be others. So I have to make it parallel. So I'm just going to, how about the sort of vector in the opposite direction, just multiplying through by -1. Or I could scale it up to 4, 6, 2. So I multiplied each component by 2, or I can multiply by 3, or divide it by 2, cut it in half. Like all those are all my options. Again, once somebody points that out that that's all you're doing, it's really obvious. But imagine, a dozen questions like this that are all mixed up, and you have to have that confidence in your understanding of planes to be able to understand what it's asking and how to do it, right? Really easy to actually answer that question once you know what it is you're supposed to do. Okay, example 2. Now it's giving us a plane in scalar form. Give a vector, not the normal, because there's multiple as we just saw, but give a vector that is normal to the plane. So the other theme that's going to come out of today is keep it easy. Like, why would you complicate things? Now I've got a 0 there because the y component is missing. That means it's 0y, right? 0 is the coefficient of the y. And done. Like, I don't need to scale that up, scale that down, do anything like that. I'm just going to use the easy one. There's no reason not to. Okay, so there you go, done. Find a vector that is parallel to the plane. So what does that mean? Here's another great example of what this is actually asking you to do is find a vector whose dot product with the normal that we just came up with, or any normal, I suppose, is equal to 0, right? So we did that in the previous unit. So I've got 3 times something plus 0 times something plus 2 times something has to be equal to 0. Because of this 0, that makes my life very easy in this case. So how about I could sub in a -2 here and a +3 here, so I get -6 and +6, and this one's always just going to be 0. So as long as the other two parts are the same but opposite signs, it's always going to work. So therefore, how about -2, 1, and 3? So I'm just plugging a 1 in there. It could also be a 0, I suppose. Or I could have been a bit more creative, -2, 5, and 3. Or how about -2 pi and 3, or e and 3, or any other value. And I don't have to just use -2 and 3. I could use others as well, but we only need one. There's a bunch of different ones. Example 3, given x, y, z equals, so now we're given vector form. Find a vector that is normal to the plane. When you have two direction vectors that are not collinear, that are parallel to the plane, the cross product will give us a vector that is orthogonal to both, right? We talked a lot about that when we introduced cross product. And so that will be a normal to the plane. Take the cross product of the two given direction vectors. So every other question we've done has been, dealing with scalar equation, but this one gives us vector form. And so now I need to know how to use vector form to come up with other properties that I need. So I'm going to take the cross product. Okay, and yes, you would write out d1, d2. This would be my d1. This would be my d2. And so it's going to be 0, 2, -1, 0, and 2, 6, 0, 2. And taking their cross product, I think I got -4, 6, -2. Therefore, I will choose my normal to be a simplified version of that if it's worth it, kind of thing, right? Okay, so there is my normal, or a normal to the plane. Find a point on the plane. If I have scalar equation, if I'm checking if a given point is in the plane, I want scalar version. That's not what I'm doing. I just have to find a point. So how about this one? Now, what's the one thing that I did here that's really important that you have to notice is I've written this with round brackets, which for us means it's a point. Now, I've probably mentioned this, but it is worth remembering that different teachers, different situations have different notation. And so, you might do some vector math in university and they don't use this standard that square brackets mean vectors and round brackets mean points. But for us at Galt, that's the way we do it, okay? And so when we want you to find a point, we want you specifically to write it as a point like that. Now, how did I actually find this point? It was the point that the position, the given position vector goes to, right? But it's also the one where when I sub in 0 for both parameters, I get that point because that is the essence of what the vector form of the equation of a line or a plane does. And similar to parametric form, I've got these two parameters. I can pick whatever values I want, and that will give me all the points in the plane or on the line, depending on what you're working with. So what if I did s equals 1 and t equals 0? Again, making it easy. It only said 1 point, but I'm going to do 2 just to demonstrate. Well, if s is 1, I've got 2 minus 1, 5 plus 0, and negative 4 plus 2. Okay, and so t was 0, so that part I didn't have to worry about, but I just took this position vector and multiplied this direction vector by a scalar of 1 and then added those vectors together. That's something we did a lot in Unit 7, just adding vectors together. It's something that we want to be familiar with. I mean, at the time, it just seemed like busy work, almost like, okay, yeah, I get to add vectors together. You just add the x's, add the y's, add the z's. Turns out that we do a fair bit of that when we start working with the properties of lines and planes, that kind of thing. And I could make those parameters any value I want and come up with other points in the plane, right? So this one just says find a point. What if it said find 3 points? Then we have to know how to be able to find more than one. I don't want to just find, or sometimes it says find a point other than the point that the given position vector goes to. So you can't list that point. Sometimes we word the question that just says, hey, you can't use the easiest one, find one other point. And I could see some people thinking that you can scale that, multiply it through by 2 or by -1, but that's not going to work. That's not the way points in the plane work. That's the way direction vectors and normal vectors work, but that's different from the position vector, right? So again, really making sure that you're visualizing this and understanding it is crucial, crucial, crucial. Find a scalar equation of the plane. Again, we're maybe noticing that there are, it often says like a normal or a directional vector or a scalar equation because you can have different ones using slightly different numbers, right? But it's no different than sort of saying the scalar equation. It's just there's not a unique one. For this one, I'm going to show you a different one. We already have the normal, so I could just punch in a position vector or a point that's in the plane. I've got 2 and use the normal vector and I could come up with it. I'm going to show you a bit of a different way of doing this, which is kind of cool. Okay, and it's going to require, you're going to notice once we do this that the math involved is very, very similar. Okay, so I am still going to use a point. So P, and I'm going to call that 2, 5, -4, which was the point from the given position vector. And I'm going to consider any other point Q in the plane. So this is a general point, so it's going to be like x, y, z, right? It's going to have x coordinate, y coordinate, z coordinate. And I am going to use that direction vector from P to Q, which is stuff we've talked about, right? And so if I have direction vector D, which is equal to PQ, where P is a known point, but Q is any other general point. I subtract backwards and I get x minus 2, y minus 5, z plus 4. Now, why am I doing this? Okay, not really a reason. Like some people are actually going to like this better. Um, it might sort of be fewer steps depending on what work you're doing in your head, that kind of thing. But I'm not trying to say that this is a better way to do it. It's just a different way of doing it. It's interesting, and it's another technique, it's another strategy, it's another way of thinking about things. We like to explore in mathematics, obviously, different algebraic ways of solving problems or just thinking about problems, and that's all this is. Okay, so this isn't necessarily a better way to do it. If you like doing it the way we did, where was it, up here, nope, not that one, this one. Okay, this was the way that we did it yesterday and that we did it so far today, where we just used the normal to write that out with our unknown d, and then used a point, some known point, to sub in and solve for d, and then restate the equation. Okay, so this is just an alternative way of doing this. Now, what do I know if I have a direction vector? This is a general direction vector to any point on the line from P. What do I know about it? I know that its dot product with n has to be 0, because I know that they will always be perpendicular. And my normal is 2, negative 3, 1, dot x minus 2, y minus 5, z plus 4. So that has to be equal to 0. So that's like 2 times x minus 2 plus, actually, minus 3 times y minus 5 plus 1 times z plus 4 has to be equal to 0. And look at this, I end up with 2x minus 3y plus z. Okay, hold on, I'm actually going to leave a space, 2x minus 3y plus z, because when I expand this, I get 2x minus 4 minus 3y plus 15 plus z plus 4. And if I compare this to the way we would have done it if we'd done it the other way by solving for d, you'll see exactly what's happening here and how this really is the same sort of process as what we did before. Like the actual computational math part of it is the same. Negative 4 plus 4 is 0, so this ends up being 15. And if you want, you can look through the solutions. I don't have to write all of those steps, so I can streamline this process and sort of make it less writing. I would say you're going to start with that line and then that line, probably, and that line. So you can sort of do it in 3 steps to get to your final answer. You don't have to then rewrite the equation because we've already got it. Okay, so some people do maybe find this a little bit less writing, or they just like it because it's kind of a cool little trick. I like the geometric interpretation of this. Like, I think it's really interesting thinking about why this works. But if you don't, if one way of doing this is enough for you, then go with that original way. It'll work every time as well. There's no necessarily benefit to doing it this way. All right, a couple more. Example 4, for the plane, give a vector that's normal to the plane. So again, keep it easy. 1, negative 2, 3. Find 2 points on the plane, A and B. So again, my recommendation is always keep things easy. And so how about I choose some intercepts? What if I set y equal to 0 and z equal to 0? Now I'm looking at that scalar equation. That's going to give me, I'll call it point A, 4 plus 0 plus 0 minus 4 is 0. So I'm really doing this by inspection. If I didn't set y and z equal to 0, if I set one of them equal to 1, that wouldn't be so bad. Setting z equal to 1 might be a little awkward. Actually, it'd be fine, depending on what the equation is, obviously. But like, you know, choosing zeros is easiest. You can choose one or two. You can make this harder and just sub in any values for X, Y, and Z that will balance this. But my recommendation is zeros always make it easy. So what if I set X equal to 0 and Z equal to 0? Rarely, by the way, do we need to come up with more than 2 or 3 points. So the intercepts are good ones to use because they have zeros in them. Or if for some reason you couldn't use intercepts, you could use at least 1 0, if not 2 zeros kind of thing. So I think that one works. So there's my 2 points, A and B. And that's what we were asked to do. I don't know where this is going. I actually do, but like this is going somewhere. But it's also just along the way asking me all kinds of different things to do with equation of the plane, all that stuff. So I've got my 2 points. This following along probably seems straightforward, but when you're just asked this on a test, just like with no context, you might forget, wait a minute, how do I do that? How do I find a point in the plane? And so we just did it by inspection, really guess and check, right? Now it wants me to find AB, subtract backwards. So that's 0 minus 4, negative 2 minus 0, and 0 minus 0. So there's vector AB, right? I can just kind of do that in my head. I don't need to show any work for that. And show that AB is perpendicular to N. So now we're seeing what the point of all of this was. The normal vector, which we already have, and any direction vector parallel to the plane will have a dot product of 0. So this was just taking us through the process of doing a bunch of stuff and then checking that this is true. Negative 4 plus 4, which is 0. Okay, therefore, AB is perpendicular to N, and AB is parallel to the plane. Direction vector between 2 points in the plane is going to be parallel to the plane, so that all makes sense. Okay, and okay, I think that's good. I think this is the last question. Example 5, given equation of the plane, said this before, you need to recognize the difference between an equation of a plane and an equation of a line. Now we often use pi for planes and we use L for lines, but they won't necessarily always have that kind of a name. You might have to name them yourself, and that's not necessarily a universal standard, although you probably would see that in textbooks and online and that kind of thing, but it's not necessary. That we always do it, that everybody always does it that way. So the better way to understand that this is a plane, it's 3 space because it's got x, y, z. That's all that tells us. But it has 2 parameters. So when I have 2 parameters, s and t, that's 2 direction vectors. That's a plane. A line would only have 1 parameter, 1 direction vector that's parallel to the line, right? So this is an equation of a plane in parametric form. Write the equation in vector form. This is the same as what we do with lines, basically, where the constants in each of the parametric equations can become my position vector to a point in the plane. And then I have my 2 direction vectors, which are going to be the coefficients of the s parameter, 3, 1, and 0, and t, and I have to use s and t because s and t were used up here, so I'm not picking those, I'm using the same ones. Negative 1, 0, and 3. And I might call this direction vector 1 and direction vector 2, right? Find a vector that is normal to the plane. How do we do that? Cross product of 2 direction vectors that are not collinear. Okay, so I've got 1, 0, 3, 1, and 0, 3, negative 1, 0. Notice how often we have to come up with we have to do cross products. Okay, so there's no way to simplify that one, no good way to make that more friendly to work with. So I'm just going to call that my direction vector. So my k was 1 in this case, right? And this is what I was saying before, is sometimes we might do something to the normal to make it easier to work with, make our lives easier, but sometimes we won't. It's just going to be the cross product. Find a point in the plane. Okay, keep it easy. How about the point to the position vector? But round brackets. I keep saying this because people keep making that mistake. Find a scalar equation to the plane. So remember, I'm going to use the technique that we did before. Scalar equation is going to be the dot product of any known point. Of the normal vector. I'm going to start with that. Dotted with this little formula, so I don't have to show this every time. Like when I used this trick before, I drew it and wrote it all out and, you know, sort of defined everything, but I don't need to do that. I can just use this almost like a formula. Okay, and so that ends up being 3x plus 6. So when I'm dotting it, it's like not quite distributive property, but doing something like that, right? Minus 9y plus 9 plus z minus 6 has to be equal to 0, and that means 3x minus 9y plus z, which was our normal, right? And it turns out plus 9 equals 0. So because I can whittle this process down to 3 steps, it might be a little bit less writing, but you know, some people might like it, but a lot of people will probably just stick with the first way that we did these. So that is day 1 of properties of planes. We're going to do another day of this stuff, and really there's nothing magic about this, just getting us used to the notation, getting us used to working with planes, and you know, thinking about the normal vector and the direction vectors, how they're related to each other, getting used to this idea that 2 direction vectors define a plane, or at least the orientation of a plane, and from 2 non-collinear or linearly independent vectors, I can determine the normal because it's orthogonal to all vectors parallel to the plane. And when I take the cross product of 2 vectors, I find a vector that's orthogonal to both, right? So you notice that almost every question had to do with the normal, whether it was coming up with the scalar equation or what have you. That's a big part of what we do with planes, okay? So keep that in mind, and that's it. The worksheet is only some of the questions. We'll use that worksheet again and do more of them. And that is day 1 of properties of planes, just working with planes, doing different things with them to get us used to it.